Hey guys, welcome back to another YouTube video on my YouTube channel. A lot of you guys, of my many subscribers, have been requesting that I do a video about both the force of the magnetic field on a moving charged particle and the magnetic field at an observation point due to a moving charged particle. A lot of you guys have been asking me to talk about that in my comment sections and my emails, so here we go. So the first one is the force, which is going to be a vector, due to the B, which is the magnetic field, onto Q, which is the charged particle. And that's going to be equal to Q, the charge value of that particle, times its velocity vector, cross product of that with the magnetic field vector. And then our other equation is going to be the magnetic field vector will be equal to mu naught, that is a constant. We're going to go ahead and divide that by 4 pi. So that whole term is going to be constant. And that's going to be multiplied by Q, the charge of that particle. Go ahead and draw a little arrow there. That's the velocity of the charged particle. And then the separation vector, that's the unit separation vector, so it's just going to be the direction with no magnitude. And that's going to be divided by the magnitude of that separation vector squared. And when we talk about the separation vector, we're talking about the separation between the charged particle and an observation point we're choosing to observe. So we can go ahead and do an example. We're going to be operating, I almost said operating, that would be embarrassing if I said that. We're going to be operating on this plane. So we got x here, this is going to be positive x. Right here will be positive y, and this will be positive z. But I'm lazy, I don't want to do anything with the z vector right now, so we're just going to say that, and that's just for reference honestly, but let's say we have a particle. It'll be a negatively charged particle, maybe it's an electron, call it whatever you'd like, and this bad boy is going to be moving rather quickly to the right, so we're going to call that positive x. I know it looks different over here, but we're going to call this the positive x direction. And that was going to be the velocity vector of that charged particle. And we're going to go ahead and kind of solve for force due to some magnetic field, some outside magnetic field onto this charge point. Side note, this charge point is also creating magnetic field, but you cannot act on yourself. You can't blow your own sail with a leaf blower and move around in a sailboat. We've all tried. So yeah, this charge, he's moving, and let's say that at that point, since we're observing exactly where that charged particle is, there is a downward, I drew that crooked, that is supposed to be directly downward. That's going to be our magnetic field at that point. So you could, if you were an ambitious person, calculate the force of this magnetic field on that moving charged particle, and it would look like this. You're going to plug in that Q value and multiply, well rather cross product the velocity vector with the, what do you call this one? The magnetic field vector. But we're not going to do that. It's a lot of work. We are instead going to just find the direction today, because I just want to talk about the right hand rule today. So the way the right hand rule works is you take obviously your right hand, you're going to point it in the direction of the first term, which here is the velocity vector. You're going to point it to the right there, and then you're going to curl your fingers down, well not necessarily down, but towards the second term, which is the magnetic field. So I'm going to have to flip my hand upside down, curl downward towards that B value, and then as you can see my thumb is pointing down into the paper. So that would be the direction of the force on that particle, except as you can see that particle is negative. So we're going to go ahead and flip the hand upside down, and then my thumb would be pointing out of the paper in the positive z direction, and that is going to be the force on that charged particle, so it's going to be in the positive z direction. So we started with a velocity vector that was positive x, and then we had a B value, the magnetic field, which was, looks like negative y. Then we ended up with a force on that particle of positive z. So now we're going to go ahead and do the exact same thing but for this. So maybe we have another charged particle, we'll call it positive q this time, and then maybe it's moving upward and to the right. So that's going to be this particle's velocity vector. And then maybe we want to observe the magnetic field due to that charge right down here. So we're going to call that our observation point. And the separation vector always points towards the observation point from the source, so it's going to be like that. And then you can, I keep knocking the paper out of the way, man. You can then do the exact same kind of concept, except here the second term is going to be the separation vector instead of the B field. So point your hand in the direction of the velocity vector and then curve it towards the second one. So it's going to kind of go this way. Awkward to do with my hand here holding the camera. So then my thumb is pointing downward. But since we have a positive Q, we don't have to swap the direction this time. So sometimes that's drawn like this. This would be into the page. This would be out of the page. But this one's going to be into the page. So the magnetic field at that observation point due to that moving charge would be in the negative z direction. So yeah, I hope that cleared up all your questions about the right-hand rule, and I hope you have a great day. So just remember to like and subscribe for more excellent physics content in the future. And yeah, see you guys.